Hi, everyone, and welcome back to Psych 3510. In this lecture, we are going to go over our second chi-square test called the chi-square test of independence. That's what we're going to spend the vast majority of our time in this lecture discussing. And then at the end, we'll spend a few slides talking about central tendency as a relevant statistic that we need to understand moving forward. So again, what we're doing here is taking all of that hypothesis testing stuff, the null, the alternative, rejecting, failing to reject. We're bringing that with us. But what we're doing is we're swapping out the specific statistic that we're going to be calculating. So you can think about that decision-making framework with the hypotheses as being consistent. That's going to, by and large, stay the same. The logic, the decisions, the way we write those APA-style conclusions, that's going to pretty much stay the same. What's going to change is the math, the statistics that we swap out for making these, helping us make these decisions. Because I like to think about statistics as a toolbox. Right? So in a toolbox, you don't have a single tool. There is no one tool that can do every job. And statistics is the same way. There is no single statistic that can answer every question. Different types of data and different types of questions require their own specialized type of statistics, just like specialized problems require specialized tools. So what we're doing is building up our repertoire of tools in our statistical toolbox. And what we want to keep in mind is being able to recognize, and this is important, not just how to use each tool, but when to use each tool. So if you have a hammer and a screwdriver, it's good to know how to use the hammer and to know how to use the screwdriver. But what's also important and critically important is seeing a problem, right, a task that has to be accomplished, and being able to correctly decide which tool do you use, the hammer or the screwdriver. So we're going to see that here with our second chi-square test of independence. Even though it's, again, another chi-square, if our chi-square test of goodness of fit was a hammer, then our chi-square test of independence is a screwdriver. And we use it to solve problems and answer questions in a very different situation than we use the chi-square test of goodness of fit. And we need to understand when to use it. So let's dive right in. The chi-square test of independence is used when we collect data on two categorical variables from the same sample. And we want to ask the question, do those two categorical variables impact one another, or are those variables independent of one another? That's a lot of words, difficult to sort of ascertain what that means. So let's look at some examples. Is your age, which we could define as young versus old, right? So categorical. We turned age into buckets, into a category. Is age, whether you're young or old, related to whether or not you use TikTok? Yes or no? So you can have young people that use TikTok, young people that do not use TikTok, old people that use TikTok, old people that do not use TikTok. And so the question we're asking is, does your membership in the category of age, is it related to your membership in the category of TikTok usage? Another example is gender, which we'll define here as male versus female, related to how you vote, Republican versus Democrat. Does your membership in category 1, gender, relate to your membership in category 2, Republican versus Democrat? Are they independent of one another, or do they impact each other? And a third example to maybe help drive the point home, we don't just have to have 2 and 2. You can have multiple options within these categories. So for example, is profession, doctor, lawyer, teacher, related to home ownership, right? Whether you own or you rent a home. So it doesn't have to be just two options within each category, right? We can have multiple options. So we could ask like, is religion, right? So Catholic, Protestant, Muslim, Jewish, or atheist related to, right, obtaining a college degree, right? So we could have, the category of religion might have 4 or 5 potential options within it. That's perfectly fine. You don't have to have just 2 in each category like we did above. You can have multiple options. So let's take this example first. We can express, let's take the example of voting and gender. Basically, we can visualize these data as a 2x2 matrix where one of the categorical variables is on top and one is on the side, such that each cell will represent a independent, or I should say a unique combination of the categorical variables. So this cell right here will have a number, and that number will tell us how many males who voted Republican were in our sample. This cell will tell us how many females who voted Republican were in our sample. This cell will tell us how many males voted Democrat. This cell will tell us how many females voted Democrat. So each cell represents a unique combination of this matrix of categorical variables. And the question at hand is, does membership in one category impact membership in the other category? A little sidebar. This is a real effect in U.S. politics. You might not be surprised if you follow politics at all, that there is an impact of gender on voting, whether you tend to vote Republican or Democrat. So if we, and I pulled real data actually from the last couple elections to show you the way this works. What I want you to do is maybe try and guess the size of this effect, a fun little game we can play. So if we polled 100 random men and 100 random women, how many of those 100 men do you think would have voted Republican versus Democrat? How many of those women would have voted Republican versus Democrat? So just take a second. It's going to be a fun little game. Try and predict what the results actually were. And then we're going to look at what the results were for the last 2 elections in 2018 and 2016 at the time of this filming. Although the 2020 election is, at the time of this filming, maybe a little over a month away from us. So try and predict. And here's the 2018 House of Representatives election results. 52% of males voted Republican, whereas 48% of males voted Democrat. And in terms of political polling, we would call that a +4 Republican lean for males. Right? So males are +4 towards voting Republican. Women had an extremely different outcome. 40% of women voted Republican. 59% of women voted Democrat. Women are apparently also more likely to vote third party, which is why this only adds up to 99. There's that hanging 1% of women who voted third party versus men who are apparently, interestingly, less likely to vote third party. So women lean +19 towards Democrats. So men lean +4 this direction towards Republicans. Women lean +19 in the other direction, which means we have a 23-point gender gap in voting in the United States, which essentially means as groups, as categories, males and females vote wildly differently from one another on average, right? Obviously, 40% of women is a lot of women, right? This is millions and millions of women who vote Republican, and millions and millions of women who vote Democrat. But the difference between male and female voting patterns is astounding. And it's relatively consistent, as we can see in 2016, if we go back to the House of Representatives election. A similar pattern for men, albeit more strongly Republican, plus 12 Republican for men. And a similar pattern for women, although less strongly Democratic. 2016 was a presidential election year. A Republican won the presidential election. And so we can see that that has sort of skewed these numbers from the 2018 election, when women were much more heavily Democrat and men were much more even or close to even. And 2018 is the midterm election when Democrats took back the House of Representatives. So this makes sense, right? These patterns hold based upon what happened in the elections. But in spite of the differences in these numbers between 2016 and 2018, we still have basically the same gender gap, a 22-point gender gap between men and women. So, see, statistics can be both interesting and relevant to important things in your daily life. Just a little reminder of that this is not trivial. These are really important things that we're talking about, and these skills that you learn can be used to assess really important questions in the world. Okay, so we're going to have some similarities in our chi-square test of independence to our chi-square goodness of fit test. So here are the things that are going to be similar. We still need to set up our null and research hypotheses. We're still comparing expected to observed frequencies. We're still going to use our chi-square table to find a critical value. And then we're still going to make a decision about rejecting or failing to reject the null and then writing up an APA-style conclusion. So those things stay the same. What changes is that now we use it in a different context when we have two categorical variables, and the math changes of how we find our expected frequencies and then compare them to our observations. So the math is going to change, but the idea that we're still generating expected frequencies and then comparing it to our observations, that general idea stays the same. A chi-square test of independence is still a comparison of expectation to observation. We just do it differently because it's a different style question. And lastly, we're going to use that chi-square table. The chi-square table doesn't change, but the way we find degrees of freedom will in fact change. So the manner in which we establish degrees of freedom on that table will change. So we'll get to all of this stuff. We'll go through this step by step with our first example that I'll walk you through. And then I'll have you, I'll probably cut it off there. And part two will be like a practice problem that you'll do at home and then I'll walk you through the answers to that practice problem. Okay, so let's stick with this example of gender and voting. So you're a political scientist studying voter behavior in the upcoming election. You poll 500 people to find out if men or women are more likely to vote Republican or Democrat. Given the data below, do gender and political party impact each other? Alpha equals 0.05. So one of the things you're going to have to do is be able to read this prompt and decide, is that a goodness of fit or is that a test of independence? So in a goodness of fit test, we are, as we discussed in the last series of lectures, a goodness of fit test compares observations to a known probability in the real world, like rolling dice, or like the 4 employees who should be chosen at random, right? There's a consistent, stable, known probability in the world that we're comparing to. In a test of independence, there's nothing about the state of the world that gives us a known invariant probability about how men and women will vote. As we saw from the actual data from 2016 and 2018, it changes, right? That those things sway and move as politics sways and moves in the country. So there isn't a known probability that we can compare to. What we're trying to do is assess whether two categorical variables, gender and political party, impact each other, or to put it differently, whether these two categorical variables are independent of one another or not. That's why we call it the test of independence. So I will provide you with these data. You will see a matrix like this on your questions or on your exam. And using these data and this prompt, you have to figure out that this is a test of independence, not a test of goodness of fit. But here are the data. These are our actual real world observations. We polled 500 people, and this is what we found. 145 males voted Republican, 90 males voted Democrat, 115 females voted Republican, 150 females voted Democrat. The question is, does your membership in a gender category impact your membership in a political category? So we can use our we can do our hypotheses in words here because it's a little tougher to use symbols for a test of independence. And the hypotheses are pretty straightforward. The null hypothesis is that nothing is happening, right? Gender does not impact political party, right? The innocent until proven guilty phenomena still applies. So the null hypothesis is that gender and political party are independent of one another, meaning they do not impact each other. Nothing is happening. The null, the zero. The research hypothesis, or the alternative hypothesis, is that gender and political party are not independent. Right? They do impact each other. So first we want to start with our observed data. And we're going to have to do some calculations sort of up and down and across this little table matrix. So make sure you pay attention to sort of the order in which we do this and where we list each specific number that we've calculated. Staying organized is going to be really important when you do this because we're going to take these four numbers and we're going to generate more numbers in order to find our expected values. And so as you generate more numbers, you need to be able to organize them effectively. So pay attention to the way that this is sort of visually organized as we walk through it. So the first thing we do is we want to have a column to total our first variable, gender, and then we want to have a row that will total our second variable, voting or political party. So basically, we just add across and we add down. So for men, 145 plus 90 means I had 235 men. 115 plus 150 means I had 265 women. 145 plus 115 means I had 260 Republicans. 90 plus 150 means I had 240 Democrats. Notice how the totals within each variable aren't equal. That's fine. When you're collecting these data as the political scientist that we're pretending to be, you can't force there to be an equal number of Republicans and Democrats, right? That's not how that works. You are assessing voting behavior. And so you can't dictate that there are equal numbers of Republicans and Democrats. And you could potentially dictate whether you have equal numbers of males or females, but we didn't here. We just want to randomly sample. And so we ended up with an unequal number of males and females as well. Perfectly fine. These totals do not have to be equal within each of our categories. So That's step one. We just do all of our totals around the edge of the matrix. We get our male total, our female total, our Republican total, and our Democrat total. So we're going to use these total rows and columns to generate our expected values. And remember, these numbers right here, this sort of internal original data, is the real data from the real world. These are our observations of the real world. These are our O's in the equation. So just as before with the goodness of fit, I give you the O's, right? That's just the data that were collected. So I will give you that in the question. What you have to do is generate your expected values, your E's. So here we need to generate an expected value for each of our 4 cells of data. So I need to figure out, okay, I had 145 male Republicans. How many of those should I have expected? I had 90 male Democrats. How many of those should I have expected? 115 Republican females. How many should I have expected? 150 female Democrats. How many should I have expected? We have a formula for that. The formula for each cell is its row total times its column total divided by n, where n equals the total number of participants, which in this case is 500. So we're going to take this little formula and do it 4 times because we have 4 cells of data. And we're going to use our total cells to help us. So let's do this first one, male Republicans. Its row total is 235, and this cell's column total is 260. So I do 235 times 260, my row total times my column total. And then I'm going to divide by n, which is the total number of participants, 500. That's where everything comes from. I'll let you look at that for just a second. And so then we just do the math. 235 times 260 is 61,100. Divided by 500 is 122.20. Now, we want to hang on to this value because that's our E. That's our expected value for that cell. So what I like to do is I like to write it in that cell in parentheses so that we know that it's the expected value. Again, organization is key here. You don't want to confuse this value with any of your other values. You want to know that that is the expected value for Republican males. You can do that however you would like. I like to just write it in that cell and put it in parentheses. Then we move on to the next cell, Republican females. The cell row total was 265. The cell column total was 260. 265 times 260 equals 68,900 divided by 500 equals 137.80. So I put that value in the cell. We do the next one. Male Democrats, their row total 235 times their column total of 240. 56,400 divided by 500 is 112.8. And lastly, our final cell, plug and chug, returns an expected value of 127.2. So now we have our observed values, which were given to us, and we have just generated our expected cell values for each of our 4 data cells. Obviously, if you have, let's say that instead of Republican and Democrat, we had Republican, Democrat, and like Green Party, or Republican, Democrat, and Libertarian Party. If you had a third option, then we would have more cells to do, right? We would have 6 cells to do instead of 4. But because each of our variables only has two options, we end up with 4 data cells. So 4 observed values and 4 expected values. Now, it shouldn't surprise you what we're going to do next. We have our O's. We were given our O's. We have generated our E's. And so now we're just going to plug them into that same formula. That's it. We're going to take each cell one by one. We're going to plug in the observed value. We're going to plug in the expected value into the E's. And then we're going to solve that right side of the equation for every one of our data cells. So all 4 of our data cells. Then we're going to sum up the chi-square values from each of our cells. So we do the right side of the formula for each data cell. It'll generate a value, and then we save those values and we sum them. We add them up, and that will give us our chi-square. So let's do it for each cell. Male Republicans. My O, my observed, my real data, my actual data was 145 male Republicans. I should have expected 122.2. So 145 minus 122.2 squared divided by E again, 122.2. Do the math, plug and chug. We get 4.25. Do it for Republican females. 115 is our O. Our E is 137.8, so it goes in both places where the E goes. 115 minus 137.8 squared divided by 137.8 gives me 3.77. And so I want to save each of these values. I'm going to end up with 4 of them, and then we're going to add them together. So you want to make sure to save them. Again, organization is key. There's a lot of numbers floating around. We want to make sure that we hold on to the right ones and know which ones we need. Cell number 3, plug and chug our observed and our expected values. Generates a chi-square of 4.61. And our final cell, female Democrats, plug and chug, generates a chi-square of 4.09. So now I have 4 chi-square contributions, 1 from each of my cells, and these numbers mean exactly what chi-square meant with the goodness of fit. The larger these values, the more deviation my observations are from my expectation. So the greater the chi-square, the more deviation from what I was expecting. And the greater the chi-square, the more likely I am to reject the null. So basically, in a test of independence, a large chi-square means that the variables impact each other. They are related. They are not independent. So if I have a large chi-square, what that means is that my observations vary a lot from my expectations. And if my observations vary a lot from my expectations, it means that your membership in, for example, gender does impact your membership in political party. So a large chi-square means they are not independent. A small chi-square means they are independent. So we add up our 4 chi-square values, we sum them, and we get 16.72. So now we're in the same place we were with goodness of fit. We need to go find our chi-square table, and we need to generate a critical value, which we will compare our chi-square, our total chi-square to. But I told you we calculate degrees of freedom differently here. Degrees of freedom, df, in this case, equals the number of rows minus 1 times the number of columns minus 1. So I had 2 rows and 2 columns, right? Because I had male and female, that's 2. And then I had Republican and Democrat, that's 2. So I had 2 rows and 2 columns. 2 minus 1 is 1, times 2 minus 1 is 1, gives me 1. So I have 1 degree of freedom for my chi-square test of independence. I'll give you a second to look at this again. So we had 2 options for gender. We had 2 options for political party. And we plug into this formula to find degrees of freedom. Again, if I had, for example, 3 political party options, like the Green Party or the Libertarian Party, then this would change. This would have been 3, and it would change my degrees of freedom. Okay. So now we have everything we need. We have my degrees of freedom equals 1. My alpha equals 0.05, which was given to you in the question. And so now I just need to find my chi-square. Right? Degrees of freedom equals 1. So I know I'm operating on this row. Alpha equals 0.05. So I know I'm operating on this column. I find where they intersect, and boom. My critical value for chi-square is 3.841. Remember, this is our point of comparison. It's our hurdle. If we are over the hurdle, then we reject the null. If we are under the hurdle, if we are less than the hurdle, then we have failed, and we stay with the null. We fail to reject the null. So we compare our calculated chi-square, which was 16.72. We compare that to our critical chi-square, which was 3.841. So here's our hurdle, 3.841. We were way over our hurdle. We cleared the hurdle, right? 16.72 is larger than 3.841. So we reject the null. And remember, we already established what our null hypothesis was. The null hypothesis is that gender and political party are independent. If we reject that null, it means we are supporting the idea that they are not independent. In other words, that gender impacts, right? It does impact. It is not independent, of political party. So we reject the null in this case, and we are going to end up concluding that gender and political party are related. Right? They impact each other. Here's our APA style conclusion. A chi-square test of independence was conducted to determine whether gender and political party voting are independent. So we introduced our test and our research question. We reject the null, and we describe our finding. We conclude that gender and political party are not independent. They are related to one another. Chi-square, paren, degrees of freedom, which was 1, comma, n equals number of participants, 500, equals our calculated chi-square, which was 16.72, and we were significant. We are statistically significant. Something is happening, right? Something is going on. Gender is impacting voting. So what that told us is that the probability of this result was less than alpha, was less than 5%. So we are convinced because we have observed an unlikely phenomena in the direction of the alternative hypothesis. Chi-square, 1 degree of freedom, N equals total number of participants equals calculated chi-square 16.72. The probability, the P of this result was less than alpha, 0.05. So the probability of the result is lower than alpha when you are statistically significant. Because remember, we are convinced by improbable, unlikely occurrences. And so we set our hurdle and we were unlikely, right? We cleared the hurdle. It is extreme enough to convince us. So we conclude with our take-home message: women are more likely to vote for Democrats, men are more likely to vote Republican. Explain it to a 10-year-old. Okay, so that's it for part one. Go back and watch this if you need to. I highly recommend it. And then what I want you to do is, on your own at home, without watching part two, I want you to try to solve this problem. Is profession independent of whether you rent or own a home? Use the data below from 600 people and assume alpha equals 0.01 to answer the question. Is profession independent of whether you own or rent a home? We have 3 professions: doctor, lawyer, teacher, and we have 2 options for home ownership: renting or owning. So does your profession impact whether you rent or own a home? So what I want you to do is, on a piece of paper at home right now, try and solve this problem. Use the previous lecture slides, use the previous lecture voiceover to walk you through how to do the calculations and make your decision, and see if you can do it on your own. Then what I want you to do is come back to part 2, and part 2 of this lecture will be me walking you through the answers to this question. That's it for right now. Thanks, everybody, and I will see you for part 2.